In this next video, I want to look at two examples in your text, and I just want to talk them out together. You really do need the pictures here to help you with them, so I thought instead of me trying to copy them and it gets messy, we'll use the ones in the book. So there are a ton of applications of trig functions in real life, and these are just two of them. So here, this following graph shows one complete normal breathing cycle. So the cycle consists of inhaling and exhaling. It takes place every 5 seconds. Velocity of air flow is positive when we inhale and negative when we exhale. It is measured in liters per second. If y represents the velocity of airflow after x seconds, find a function of the form y equals a sine bx that models airflow in a normal breathing cycle. So they're giving you the base model that we should be using here. We're using a sine function, and you can see this does match the graph of the sine function, right? That typically starts at 0, 0. And we do, so your A is your amplitude. Notice that there's no vertical shifts or anything here, so you're starting where you're supposed to. The amplitude is really just how the max and min are being affected then. So if there's no vertical shift, you don't have to worry about that affecting the max and mins. So it's just that amplitude piece. So if I look at my graph here, my max is at 0.6 and my min is at negative 0.6. And again, there's no vertical shifts. So that is going to give me my amplitude. Instead of going from positive 1 to negative 1, I'm only going 0.6 to negative 0.6. So my A there is 0.6. That is going to be my amplitude. I am going to note too that it goes in the same order, right? So the sine function typically goes up first and then down. If it went down first and then up, then your amplitude should be negative because you're getting that vertical flip. So our A here is going to be 0.6. Now the B part affects the period. Remember, the sine function typically has period 2 pi, but this one here, this completes one cycle of the wave in period 5, which is not 2 pi, right? 2 pi is what? 2 times 3.14, so a little over 6. So we need to figure out what the B value is based on that information. And what you can do here is you can remember that we can find the period by using the formula 2 pi over b. So from the graph, I can see that the period is 5. I know 2 pi, and I don't know the b. So what we can do is we can solve a little equation here. Multiply by b on both sides, divide by 5, and we can get our b value that way. So we kind of reverse solve that part of the equation. And then we're done. We have our A, we have our B, and we can just plug it back in and get our sine graph. I'm going to show you another example here. And again, I just want to kind of talk these through. I don't know that it's worth, I mean, you should definitely take notes on it, but I don't know that it's worth me trying to redraw these pictures. They get pretty messy. So I'm going to do another example. Again, we'll talk through the process. So this one is tides, and tides are also cyclical like this. Excuse me. So here your figure shows the depth of water at a boat dock as it varies with the tides. So the depth is 5 feet at low tide and 13 feet at high tide. On a certain day, low tide occurs at 4 a.m. and high tide at 10 a.m. And obviously that does change day to day, so this is on a particular day. Y is going to be the depth of the water in feet, and X is hours after midnight. And we're going to use a sine curve to represent this. This one is a little bit more complicated. It has multiple changes here, so it actually has all 4 changes to model the water's depth. Now you're working backwards here. Normally when we're graphing an equation, the vertical shift is the last thing that you sort of take into account. When you're working backwards, that's really the first thing you have to take into account. Or it's one of the easiest things to take into account first. Now, normally a sine curve kind of centers at 0, right? Or centers on the x-axis, and it goes above and it goes below equally. So clearly this has a shift because we're not centering at 0 like we did in the last example. We're way up. So we do have a shift here. If I notice the center of that graph is at the value 9. So instead of the center of the graph being at the value 0 and lying along the x-axis, it's at 9. So that means the vertical shift is 9 units. And it's positive 9 because we went up. So your D value here is going to be 9. The other thing you can figure out pretty easily from the graph So the amplitude can also be found pretty easily from the graph, and that has to do really with how tall the wave is. So if 9 is that center here for a second, just kind of think about it that way. From 9, it goes up to 13, or from 9, it goes down to 5, and you can see it's the same change. From the center of that wave, it goes up 4 units, and then it also goes down 4 units. So that change of 4 is going to be your amplitude. So our A value is going to be 4 here. Now, for the period, you need to figure out one cycle. And we are doing the sine curve. So they have the blue part highlighted because this is a sine curve. So it does kind of start in the middle, go up, go down, and then back up for that one cycle. However, you don't need to have those exact points to find the period, really, as long as you can find where the pattern changes. You can find the period that way. So for me, it was much easier to look at the 2 low points or the 2 high points. So the 2 low points, I went from 4 to 6. So that was a change of 12. And the 2 high points also went from 10 to 22, which is also a change of 12. So I found the period that way. Again, I know it's not quite the starting and ending point that we normally think about for a sine curve, but as long as you can find the pattern of where it starts to repeat, use any points that are easy. So that period there is 12. And then we were able to use that same formula we did in the last example. 12 equals 2 pi over b, multiply by b on both sides, divide by 12, and we're able to get the period, the b value is pi over 6. So at this point, we have found the A, the B, and the D. So the last thing we have to figure out here is the C, which has to do with the phase shift. So remember, the phase shift is C over B. Now, this is where it's important to know the general shape of the sine curve. So the sine curve does kind of start in the middle. It goes up, down, and back up again, right? So the first time we really see that piece is right here. So they tried to highlight in blue for you where you kind of first see that sine curve. And what you should notice is that normally, a sine curve starts over here at 0 on the x equals 0, but it's starting over here. So that change has to do with your phase shift. Now, this number I think is really hard to see. I really think they should give you that value there, or else it's a little difficult to figure out exactly what that number is. So it's between 4 and 10. I had estimated it more at 6, but I guess it is halfway, so it would be 7 is the halfway point there. So that is a change of plus 7. So what we did here is a similar thing to the period, and we were able to use that change of 7 units there and solve C over B, which is the equation for the phase shift. Your B was pi over 6, so we multiply 7 by pi over 6, and we have our C. So that's probably the hardest one to find. You have to be just really careful how far over the start of that sine function is going. Here it was 7 units, so that's why we use 7 when solving. And then you're able to go ahead and plug in those values to find your question. Now, I will say that technology can do this stuff for you as well. So a lot of our graphing calculators have regression features which allow us to find the best curve given some points. Usually you need at least a few points that you can plug in. I think you need at least 4 or 5 in order to do it for the sine curves. But a lot of technology can do this for you. So you don't have to always rely on by hand techniques to do it. Realize, when graphs get much more complicated in the real world, we do have technology that can help us find these equations as well.